Hello gems! Welcome back to another video of A series. In this video, we'll be discussing the previous year questions from the chapter of atoms. Now, atoms is one of those chapters which we couldn't discuss in 2021 and here we are discussing it now, okay? So, let me tell you, in 2021, we have covered up a lot of previous year questions from different topics. You can check out the playlist in the description box of this video, okay? And if you are here for this specific video, let's get started. So rule number 1 of A series is that we begin with the super easy category, right? So here is question 1 from the super easy category from 2014. Okay, so what is the angular momentum of an electron in the nth orbit? Such a simple question, right? It's directly based on your Bohr's postulate, right? You can basically write your angular momentum as an integral multiple of h by 2 pi, right? So angular momentum in a general sense is given as nh by 2 pi, okay? And for nth orbit, yeah, it's nh by 2 pi, that particular orbit number into h by 2 pi, right? So the correct answer over here is option C. You are just supposed to know the Bohr's postulate in order to crack this question, right? Such a simple question. Now coming to question number 2, angular momentum, again it's the same thing, of an electron in the first orbit. Again, very simple. You are just supposed to substitute n equals 1 over here, right? And you'll get it as h by 2 pi, right? So basically this n represents the orbit number. Here the orbit number was n, okay? Here the orbit number is first 1, okay? So substitute 1 over here, so that will give you h by 2 pi. So the angular momentum over here is h by 2 pi. Again, option C. That's the correct choice over here. I know this question sounds silly because they are from the super easy category. We'll level up. Don't worry, this video is not made for kids. Okay, let's move to the next questions now. Coming to our next set of questions, in question 3, which is from 2006, you are asked for the de Broglie wavelength. Yes, I pronounced that right. Okay, so de Broglie wavelength of an electron in the first orbit of hydrogen atom. Okay, now there is a relation between the de Broglie wavelength. Basically, if you see, electron is also like a wave, right? That is what you learn in the chapter 11, dual nature of radiation and matter. But basically, okay, so it also has a wavelength. Okay, so de Broglie wavelength of an electron, you are asked for its wavelength in the first orbit. Okay, so now there is a relation between the de Broglie wavelength and the size of your orbit. Okay, or basically a relation between the radius of your orbit and de Broglie wavelength. And the simple relation is that 2 pi r equals n lambda. Okay, in this case we know that n is the orbit number, okay, r is the radius of the your orbit, okay, and lambda is of course the de Broglie wavelength. Okay, so you can see the relation, right? It's between the size of the orbit and de Broglie wavelength, right? So in this case we have the first orbit, so 2 pi r will be equal to lambda, right? So basically the de Broglie wavelength of that electron in the first orbit is nothing but equal to the circumference of your orbit. Okay, so option B is equal to the circumference. That is the correct choice over here. If you want to visualize this, I can draw it for n equal to 3. It is also shown in NCERT if you have ever opened it up. Okay, so suppose you have the third orbit over here. Okay, this is an H-like atom. This is the third orbit. Okay, and in that case, what will be this thing? It will be 2 pi r equals 3 times of lambda. Okay, so the entire circumference will be covered up by 3 wavelengths. Okay, let me show you how. So this is one wave, right? One wavelength, second wavelength, right? And from here we have the third wavelength. Okay, I could not draw it symmetric. I'll try again. Okay, let me try again. Okay, so again, start again. It's the third orbit. Okay, so this is the first wave. Fine, this is the second wave. Okay, I think now it's symmetric. And this is the third wave. Okay, you get the point, right? So for the third orbit, the circumference will be equal to the 3 times of de Broglie wavelength. In our case, it's the first orbit, so basically n is 1. So 2 pi r, the circumference will be equal to the de Broglie wavelength. Okay, and that's our answer over here. Okay, I hope you can visualize it better now. Okay, let's come to question number 4. The total energy of an electron in the first excited state of each atom is given over here. It's minus 3.4 electron volts. You are asked for the kinetic energy. Now you are just supposed to know the relation that total energy and kinetic energy just differ in signs. Okay, so total energy equals minus of kinetic energy, or kinetic energy equals minus of total energy. Okay, they are same in magnitude but they differ in size. Okay, so the correct answer over here will be negative of this, which will be positive 3.4 electron volts. And for those who are curious what is the relation between total energy and potential energy, basically total energy is potential energy by 2. Okay, they have the same sign, both of them are negative, both are negative, but when you divide potential energy by 2, they differ in magnitude. Okay, potential energy and total energy, they differ in magnitude. So when you divide potential energy by 2, you get total energy, whereas total energy and kinetic energy differ in signs, not in magnitude. So these two things are important to remember over here. Okay, and that gives us our answer. Let's move to the easy category now. So question 5 and 6 over here. Now take a note that we have increased the level. The questions are from the easy category now. Okay, so question 5 over here from 2018. So if n equal to 4 was the last shell, okay, so they have restricted the shell number to n equal to 4, then what would be the number of possible elements? Okay, in this case, wherein we have restricted the shell number to n equal to 4, currently we have n equal to 7, right? That is what I guess. Okay, so if we had restricted it at n equal to 4, the last shell number is n equal to 4, you can't go beyond that, then what would be the last possible element? Okay, so basically they are asking you for the atomic number of the last element, because that is the thing that shows the position in the periodic table, right? So atomic number of the last element will be nothing but the number of possible elements, right? So let's find out the atomic number. Now one long way of doing this is jotting down all the shells and subshells, right, and then filling them up, right? You can go for from 1s to s to p all the way down. The last subshell will be 4f, right? So you can fill up all those subshells, okay, shells and subshells, and then add all the electrons which are in them, okay, and that will give you your answer, right? But that is a long way to go, and we'll use a shorthand approach over here. The approach that we are going to use is a formula. We'll just use the formula that number of electrons in a particular shell, okay, in a particular orbit. So number of electrons in an orbit is basically given as 2n square. Okay, 2n square. Basically n is the orbit number. Okay, so and now we'll write it for different orbits from 1 to 4. We'll add them, and that will give us the number of electrons in all the orbits from 1 to 4, and adding those up basically gives us the atomic number of the last element, or all the possible elements that are there in this case. Okay, so let's write it. For n equal to 1, we'll have this, right? For n equal to 2, we'll have this. So basically we are adding the electrons in all the shells and subshells. So n equal to 3 over here, n equal to 4 over here, right? So if you want to confirm now, you can check it for n equal to 2, n equal to 2, 2n square, right? So this gives you 4, and 4 2s are 8. Okay, so if you see the second shell, okay, you have 2p and you have 2s and 2p, right? In s you have 2 electrons, and in p you can have 6 electrons, right? P, x, y, z, and in those you have 2 electrons each. So in your p subshell you can have 6, and in your s subshell you can have 2. 2 plus 6, 8, 8. Okay, so this formula is correct. It gives you the correct number of electrons in a particular shell. Okay, now just add this up, and that will give you your answer. 2 plus 8 plus this is 9, 3, this is 9. Okay, 9 into 2 is 18, and here 16 into 2, 32. Okay, this gives us 10. This gives us I guess 50. Yes, so 50 plus 10, 60. So option A, 60 is the correct choice over here. Okay, of course you can go by the long way of jotting down all the orbits, or you can remember this formula. Okay, it's a very helpful formula. Okay, the number of electrons in a particular orbit is basically given by 2n square. This is also something you learn in chemistry, okay, but who cares about chemistry? Coming to question 6, you are told that an electron jumps from n2 to n1. Now n2 may be some excited state, n1 is ground state maybe, okay. You are told that n2 is greater than n1. You can see it from here as well. So the radius of n1 is radius of n2 by 4, or radius of n2 is 4 times the radius of n1, okay. So basically n2 has a bigger size, it's a bigger shell as compared to n1, okay. You are told that the velocity of the electron in the n2 shell n2 is v. Then you are supposed to find what is the velocity of that electron in n1 shell in terms of this v, okay. Now here you are supposed to know certain formulas which are a little bit subtle, okay. Let me tell you those formulas, where r is given as n square h square epsilon naught upon pi m z e square, okay. Now you know what is the best part of life? Repetition, okay. So r equals n square h square epsilon naught upon pi m z e square. R equals n square h square epsilon naught upon pi m z e square. R equals, okay, I'm not doing that again, okay. So basically you get the point. You have to remember this either by repetition or write it down somewhere, okay. Write it down now, okay. Now one more formula that we are going to use over here is the velocity one, okay. What is that? I also forgot. It's z e square upon 2h epsilon naught n, okay. And again z e square upon 2h epsilon naught n. Z, okay, not doing that again. Okay, so basically these are the two formulas that we will use in our discussion in this question, okay. Actually, not the purely the formula here. Even if you knew that r is directly proportional to n square, you can see that, and v is inversely proportional to n, that would do, okay. Only this logic you are supposed to catch over here. Anyways, to be on the safer side, you are supposed to remember this formula. And what is the way? You know it, okay. So yeah, so in this question we'll not need the formulas, so I am going to erase them. You can note it down, you can pause the video here, okay. If you missed it, you can rewind it, okay. So the thing that we are going to use is this relation, okay. R is directly proportional to n square, all others were constant, h square epsilon naught, what is that, n square h square epsilon naught upon pi m z e square, all others were constant, right. And in similar fashion, your velocity is inversely proportional to n, all others were constants, okay. So from this relation I can write uh, radius of r n1, okay, the radius of n1 by radius of n2 is 1 by 4, right. I also know that your radius is directly proportional to the shell, right, shell number n, right, it's square. So I can write this as n1 by n2 the whole square, right. Since it's a ratio, the proportionality constant will cancel, okay. So here we have the important thing, right. So n1 by n2, so first we use this relation, then we substituted in terms of n, right. So now we know that radius is directly proportional to n square, so n1 by n2 the whole square will be equal to 1 by 4, okay. So that is clear over there. So from here you can in fact find n1 by n2, it will be just the square root of that, that will be half, right. And now the next relation that we are going to use is this one, right. So v in, basically we are supposed to find v in n1, so v in n1 by v in n2, okay, velocity in orbit number 1 divided by velocity in orbit number 2, that is inversely proportional to the orbit number, right. So inverse relation, so n2 over here by n1 over here, okay. So you can see the inverse relation n1 n1 n2 n2, right. So inverse relation vn1 by vn2 is n2 by n1, okay. Now you already know what is n2 by n1, you can directly find it out from here, it will be 2, right. So n1 by n2 is half, so n2 by n1 will be 2, of course. And from here vn2 is v, right. So vn1 is basically n2 by n1 is 2 and vn2 is v, okay. So take it to the other side, so 2 times of v, okay. So the velocity will double in the below orbit, in the n1 orbit. Yeah. Okay, so Vn1 is 2 times of V. That is the correct choice over here. Again, you are supposed to remember those formulas and you know the way, right? Oh my god, I'm just repeating it over and over again. Let's go to the next question now. So question number 7, in this question you can see a particular transition and the wavelength associated with that particular transition. So basically electron jumps from n equal to 3 excited state to n equal to 1 in an H atom, and a photon is released, right? So the wavelength of that photon is this, okay? And for this particular transition the wavelength is this. You are supposed to tell what is the ratio of these two wavelengths, okay? So the simple formula that we are going to use over here is 1 by lambda equals, I'll write that properly, 1 by lambda equals r z square upon 1 minus the final orbit square, okay, minus 1 upon the initial orbit square, okay. So that is the formula that we are going to use. I hope you know it. So 1 by lambda, let's write it for the first one, lambda 3 to 1, okay. So the transition is from 3 to 1. So r z square, I'm not putting the value of r, it will basically, we want the ratio, right? So that will cancel out. So z square, basically H atom, 1 square, that is 1, okay. Z is the atomic number, 1 divided by n final square. Finally the electrons end up in the first orbit, so 1 square, that is 1, minus 1 upon n initial square. Initially it is in third one, right? For this one it is in third one, so that is 9, okay. 3 square 9, and 1 minus 1 by 9, that will be, so 9 minus 1, 8 r by 9, okay. So this is the wavelength, okay, or the reciprocal of wavelength for this one, or we can write the wavelength from here, okay. I'm just making the reciprocal, so it is 9 by 8 r, okay. So this is what we get. Now similarly let's do it for 2 to 1, okay. So for that it is r z square, z is again 1, and it is from the finally it comes to 1. Initially it is from 2, so 2 square is 4, okay. So 1 minus 1 4, that will be 3/4, so 3 r by 4, or you can write lambda 2 to 1, so basically take the reciprocal, so 4 by 3 r, right? So now you have the two terms, you are just supposed to take the ratio, right? This divided by this, right? So let's do that. Lambda 3 to 1 divided by lambda 2 to 1, so that will give you 9 by 8 r, and this, just make the ulta of that, so that will be 3 r by 4, right? So r and r will get cancelled as I promised. So 9 3s are 27 and 8 4s are 32, okay. So 27 by 32, option A is the correct choice over here, okay. So direct application of this formula and taking ratio, okay. That is all what we did. You'll see a lot of these questions in our discussion ahead today. So the transition type of questions are the favorite questions of your BITSAT. This formula itself is the favorite of your BITSAT, okay. So please note it down somewhere, and let's move to the next question now. So question 8 and 9 over here, we are almost halfway in our discussion. I hope you are enjoying it. If you are enjoying it, smash that like button, okay. So let's come to question number 8. Here we are told that lambda 1, lambda 2, lambda 3 are the shortest wavelength for Lyman, Barmer and Paschen series respectively, okay. Then you are supposed to find what is the ratio of lambda 1, lambda 2 and lambda 3. Again, the same formula we are going to use. And the thing over here is that you are just supposed to know that energy and your wavelength are inversely related, right? The energy of the photon that is emitted is hc by lambda, right? Energy is inversely proportional to wavelength, okay. So basically here we are told about shortest wavelength, right? So the energy transition for this wavelength will be the largest, okay. So that is the point to catch over here, okay. Shortest wavelength means largest energy gap, okay. So that is the idea over here, okay. So for Lyman series we can write 1 by lambda, okay. What is the formula? 1 by lambda, it is r z square upon 1 minus n final square minus n initial square, right? So this is the formula that we are going to use. So the shortest wavelength first for the Lyman series, which is 1, right? Lambda 1, that will be r z square, Okay, I'm not substituting the constants, into 1 upon what is the final shell for Lehman series. Finally, the electron falls to n equal to 1, right? The n final for Lehman series is 1. I hope you know this. N final for this series is 2 and n final for Paschen is 3. Okay, so Lehman, Balmer, Paschen, bracket P fund. So 1, 2, 3, 4, 5. So that is the number of n final for each of them. Okay, so n final is 1 for Lehman. So 1 divided by 1 square. So that is again 1. Okay, minus 1 divided by, now we are searching for the shortest wavelength, right? Shortest wavelength, I told you, it will be the largest energy gap. Okay, so basically you want the largest energy gap, so why not take infinity? Okay, so that will give you the transition from infinity to 1, right? So basically at a quantum size, the infinity is not that big. Okay, so basically this will give you the largest transition, right? So largest transition, shortest wavelength. Okay, so that is the idea over here. So basically this term will become 0. So 1 by lambda 1 is rz square. Okay, similarly we can proceed our discussion for 1 by lambda 2 for your Balmer series. So rz square, here n final is 2, right? So n final is 2, so that will be 2 square 4, and again 1 by infinity square, that's 0. Okay, I'm not writing it now. Okay, you know it's 0, right? Okay, I'll write 1 minus 0. Okay, 1 by 4 minus 0, so this is rz square by 4. Okay, now again you can write 1 by lambda 3 for the third one, rz square into 1 minus nf square. Nf for this one is 3, so that is 9, and again minus 0, 1 by infinity square, that is again 0, right? So rz square upon 9. Okay, so you can easily see you have to take the reciprocal actually. So lambda 1 is 1 by rz square, and similarly here you also have to take lambda 2 is 4 by rz square, and lambda 3 is 9 by rz square. So when you take the ratio, you can easily see that it will be 1 rz square, rz square, rz square will get cancelled, and you'll be left with 1, 1, 4, 9, right? So basically lambda 1 is to lambda 2 is to lambda 3 is 1 is to 4 is to 9, right? 1 is to 4 is to 9. Okay, or basically you can see it from here. Basically the shortest wavelength, we are saying it's the largest energy transition. So n initial, by this we mean that n initial is infinity. Okay, so initially it's starting from infinity in a way. Okay, so 1 by lambda is rz square upon, so this term basically becomes 0, right? N initial is infinity, this becomes 0. So only thing we are left with is n final square. Okay, these two are constants. You can see that 1 by lambda is directly proportional to 1 by nf square, or lambda is directly proportional to nf square. Okay, this is 1, 2, 3, and a lambda is proportional to their squares, right? So 1 is to 4 is to 9. 1 square 4 square 9. Okay, so that is the short trick over here. We can also apply the short trick in this question now. The series limit, now again series limit means the same thing. It's the shortest wavelength for a particular series. Okay, so series limit for Lehman series, okay, which is this one, it is given as 912 angstroms. Okay, now they have given you the value for that particular wavelength. Okay, so they are given you this value. Okay, now again series limit, you are supposed to find what is the series limit for Balmer series, right? Now we directly know that it's directly proportional to the square of those, right? So square, it will be proportional to the square of n final. N final for Balmer series is 2, so it's proportional to we'll say 4. Okay, for Balmer series it will be 4, so 4 times this, so 4 times this is option C. Okay, for those who are scratching their head, let's do it again. So 1 by lambda 1, so we'll say the series limit for this one. Okay, that is rz square into 1 upon, for Lehman series n final is 1. Okay, and this minus 0. Okay, so you get lambda 1 is 1 by rz square, basically the same thing that we got over here. Okay, now for 1 by lambda 2, we'll say it's Balmer series. Balmer series we have already calculated it, right? So that is 4 by rz square, right? Again you have to do the same thing, and yeah, the same, pretty much the same thing. and lambda 2 will be given as 4 by rz square, right? Now you can take their ratio, so rz square and rz square will cancel. We want lambda 2, right? So lambda 2 by lambda 1, so that will give us 4 by 1, right? So lambda 2 by lambda 1, rz square cancel, 4 by 1, right? So you can see easily see that lambda 2 is 4 times of lambda 1. Lambda 1 they have already provided you, it's 9 to 8, right? So 4 into 9 to 8. So option C, 4 into 9 to 12 is the correct choice over here. I hope you are able to catch the shortcut, or at least this discussion that we did. Okay, so that is it from the shortest transition questions, sorry, the longest transition, shortest wavelength questions. Let's move to the next section now. Okay, so just one question before we go to the easy moderate category. So question number 10 from 2010. Okay, here you are given the wavelength lambda of the third line. Lambda is the wavelength for the third line of Balmer series for H-like atom. Okay, it's not hydrogen, but it's H-like atom. Okay, you are supposed to tell what is the ground state energy of that atom. Now, ground state energy is basically given as minus 13.6 z square by n square, right? So here if you see, if it was hydrogen, both will be 1, ground state n equal 1, and z would have been 1 for hydrogen, and it would have been 13.6. Now the catch is it's H-like atom, it's not hydrogen, maybe not. Okay, so first thing is that we are supposed to find z through this data that is provided. Okay, and how will we do that? Basically using the same formula, 1 by lambda equals rz square into 1 upon n final square minus 1 upon n initial square, right? So use this formula over here, find out the value of z, and then substitute it over here, and then you'll find what is the energy in ground state, right? In ground state, basically n is 1. Okay, we are just supposed to find this z. Okay, so from here 1 upon lambda equals rz square. Okay, I'll substitute the values in a while. Okay, so this is 1 by if you see third line of Balmer series. Now first line of Balmer series is, let's see what transition it corresponds to. So first line, basically in Balmer series, everything will end up at 2, right? Everything ends up at 2. So initial, okay, let me write it this way, and final is 2. Okay, this is constant for Balmer series. So n initial for your, you can see the first transition is from 3 to 2, right? That is the most basic one. Second one can be from 4 to 2. Third one will be from 5 to 2, right? So this is the one that we are talking about, right? So n initial is 5 and final is 2. And final is always 2 for Balmer series. We just wanted to know what is the value of n initial for the third line. If you see the third line, it corresponds to 5 to 2. Okay, so first is 3 to 2, second is 4 to 2, third one is 5 to 2. Okay, so substitute it over here. Final is 2, 2 square 4, minus initial is 5, 5 is square it 25. Okay, now just solve it. So 1 upon lambda, I'll substitute the values in a while. So this is 100, 25 minus 4, that is 21. Okay, fine. Now let us solve this. Okay, so 100 upon 21, upon here you'll have lambda, and here you'll also have 1 by r. Okay, this is into, okay, so 100 upon 21, lambda also you have, r comes over here, and this will give you z square, right? So now just a trick guys, 1 by r is 912 angstroms. Okay, so this is something that you should remember. Even if you don't remember the value of r, it's okay. 1 by r is 912 angstroms. Okay, so 912 over here. Okay, I will write it as into 10 to the power minus 10 in SI units, into 21 into what? Into lambda. Okay, this is lambda. 1 by r we have already substituted. We are just left to substitute lambda, which is 108.5. Okay, and that is in nanometers Now you have to cancel this, you have to calculate this out, and this will come around 4. Okay, so z square will be around 4, so z is around 2. Okay, trust me on that. So z value is 2 over here, and you are just substituting z over here, and that will give you your energy in the ground state. Okay, so energy in the ground state basically will be 13.6. Okay, here if you see, they are only concerned about the magnitude, into z square. Z is 2, so that is 4. So z square basically, when you calculate this, it's approximately equal to 4. Okay, divided by n square. N is a ground state. Ground state means n equal to 1. Okay, so 13.6 into 4, what is that? I think that should be close to 13 4s are 52, so that is close to 54. Okay, so option C, 54, is the correct choice over here. Okay, I hope this question was clear. I hope this thing was clear. Okay, and that is how you do this question. Let's move to the easy to moderate category now. So question number 11 over here from 2017, the first from the easy to moderate category. Now in this question, some radiation of particular wavelength is incident on a hydrogen gas. Okay, now in this case, the number of spectral lines that were observed were 6. You are supposed to tell what is the wavelength of the incident radiation. Okay, so from this you can take a guess that the formula that we are going to use is 1 by lambda, again the very same thing, rz square upon n 1 into n final square minus 1 upon n initial square, right? So if you see, we are provided a little bit of data over here, each atom. So z square, z is 1, z square is 1. Okay, r also, it's a constant, we know its value. Okay, we know 1 by r, right? So the thing that we are supposed to find is n final and n initial. Now there is a formula for this, the number of spectral lines observed. So number of spectral lines, okay, is given as n, it's n initial minus n final into n initial minus n final plus 1 upon 2. Okay, this is the formula that I want you to by heart. Again, a lot of formulas. Okay, formulae. Okay, so here we'll take n initial as 1. Okay, although it's not mentioned clearly, but we'll assume that the atom finally comes to ground state. Okay, so that is the basic state. So wherein in questions, when you are not mentioned the final state, okay, sorry, it's the final and final state, we'll take it as 1. Okay, we'll assume that the atom finally comes to its ground state, right? That is what happens when the electrons are excited. Okay, it finally comes to the ground state, okay, after a series of transitions, right? So when you substitute this nf as 1 over here, you'll get n minus 1. Okay, I'll write n initial as n only. Okay, you'll get to know why, because we'll get a beautiful formula over here. Okay, n final is 1, so plus 1 minus 1, right? So n again. So this is one more formula, one more version of this formula. This is the more general one. If you are asked for transitions between two random states, suppose 2 and 3, then you can use this formula. If you are asked for transitions from 4 to 1, 2 to 1, 3 to 1, in that case, wherein n final is 1, in that case you can use this formula. Okay, I repeat, when n final is 1, you can use this formula. Otherwise, this is the more general one and applies everywhere. Okay, so that is the formula for number of spectral lines. Okay, now this is given as 6, right? Number of spectral lines is 6. Okay, now this n, I'll write it as n initial only. Okay, so here you'll get 12. So n initial square minus ni. Okay, so n initial square minus ni plus or minus 12. Okay, so this is the equation that we are supposed to find. That will give us the value of n initial. We'll substitute it over here, and that will give us r lambda. Okay, so that is the whole idea of this question. Okay, so 12. I think it's 3 4s, and that will be minus 4 plus 3. Okay, so these are the factors. Okay, so now your initial state n, the number cannot be negative, so this is discarded. Only this one is kept, so this will give you ni equal to 4, right? So now this just substitute this over there, and you'll have your answer for lambda. So 1 by lambda is r, n final is 1. Okay, we have taken it as 1, and n initial we know it as 4 square, that is 16, so that will give you 15r by 16, right? So that is 1 by lambda. If you want lambda, that is 16 by 15r, right? Now you already know that 1 by r is, let us solve it over here. Okay, 1 by r is 912. Okay, please remember that. So 16 by 15 into 912. Okay, so this cancels by 3, 3 5s are 3 3s are 3 zeros are 3 4s are. Okay, and again, if this was suppose 300, suppose this is in angstroms, right? So 5 6 are. Okay, so now 16 6 are, that is 96. So around 960 angstroms. Okay, so we decrease the value, so this should be a little bit more than that. So option C, it's a shot in the dark, but I'll take it. Okay, so I think option C, 975 angstroms, is the correct choice over here. Okay, I hope you knew this formula and this is the way to do it. Okay, this is one more good formula, please note it down. And yeah, we'll do more on spectral lines just in a while. Okay, so let's move to the next question now. So question number 12, in this question you are told that one of the lines of this atom, this is a hydrogen like atom if you see, okay, has a wavelength lambda. Now this lambda corresponds to transition from 12 to x. Okay, so initially the electron was in the 12th orbit, it comes down to the some x orbit. Okay, you are supposed to find that x. It is also given that this wavelength is equal to the second line of the Balmer series. Okay, that particular wavelength of the Balmer series. Okay, so this is the data that we'll use in order to find x. Okay, so again the same formula that we are going to use, 1 upon lambda. First let's write it for this one, lithium, right? So r z square, lithium is hydrogen, helium, lithium, right? So atomic number 3, right? So 3 square 9, okay, I've squared it, upon 1 minus n final square, n final square, so basically it comes down to x, right? So x square upon initial square is 12. So yeah, that is the thing. Now for each atom you can write 1 upon lambda. Now lambda is the same, so their reciprocal is also the same, of course, right? So 1 upon lambda equal to r z square. Z square is 1 square, so leave it. Okay, and then 1 upon n. Now n final and n initial for the second line of Balmer series, right? First line we know that, first of all we know that n final for Balmer series is 2, right? So the first line will be from 3 to 2, second line will be from 4 to 2, of course, right? So this is the transition that we want, right? So n final it's 2, so that will give us 2 square 4, and here initial it's 4, that will give us 4 square 16, right? Now you just have to equate this two, right? Because they have the same wavelength, it's given in the question. So 9r, and solve this. This is 144 x square, and here you'll have 144 minus x square. Okay, and here you'll have, so I'm equating this two, okay, the right hand side. So r, and wait, so this is 16 into 4, or I can take 16 common, right? 16 is the LCM, and that will be 4 minus 1 3. Okay, so 3r by 16. Okay, now this and this can get cancelled. Okay, 16 9s are 144, 9 and 9 will get cancelled. Okay, now we have few things left over here. 144 minus x square upon x square, that x square we can take it to the other side, so we have 3x square. Okay, from here we'll have 144 equals 4x square. Okay, now x square will be given as 144 by 4, 4 3s are 12, and 2 remains, 4 6 are 24, right? So x square is 36, or x is basically 6, right? Only taking the positive value because it's the value for nf, right? That can be only positive. Okay, so basically the value for x is 6. Option C, 6 is the correct choice over here. Okay, so we just wrote the formula for this transition, right? It's from 12 to x square, and then for this transition, the second line of Balmer series, right? we know it's from 4 to 2. Okay, that transition, equated those as it was given in the question. Okay, then solve an equation and then found the value of x. Okay, so that is the thing we did. Let's move to the next question now. So question number 13 over here. In this question, each atom is excited by a particular radiation of this wavelength. Okay, you are supposed to tell what are the number of spectral lines observed in this case. Now you already know the formula for this. Number of spectral lines is given as n into n minus 1 by 2, right? This is when n final equals 1, right? Otherwise you have that very general formula, n initial minus n final into n initial minus n final plus 1 divided by 2, right? When n final is 1, this is the formula, right? N initial minus n into n initial minus 1 upon 2. Okay, now this is the formula that we'll use, because we'll assume that n final is 1. Okay, it's not mentioned in the question. So whenever there is a question, I told you about this, wherein it's about spectral lines and nf is not mentioned, you can take it as 1, because we are assuming that finally the atom will come to its ground state. Okay, so n final is 1, we can apply this formula now. But the problem is we don't know what is n initial in this case, right? We don't know what is the value of n initial. Okay, and how will we find it? If you can see, here is the clue. Okay, we are supposed to use the same formula. 1 upon lambda is r z square. Now it is h atom, so z is 1, and 1 upon n final square, n final is 1, so 1 upon 1 square, that is 1, minus 1 upon n initial square. Okay, let's take n initial as x. Okay, so that will be 1 upon x square. Okay, now what can we do? We can take this 1 by r and I'll multiply lambda over here. 1 by r, we already know it as 912, right? 912 angstroms, and here also we'll put the value in angstroms, right? It's in angstroms. So here you'll have x square minus 1 upon x square, right? So 912 into x square, just cross this, and here you'll have 970.6 into x square minus 970.6, right? Yes. So here, from here you can get 970.6 x square minus 912 x square is equal to 970.6. Okay, I just took it this to this side, this to that side. Okay, now when you subtract this, you'll get around 58, right? Around 58. X square is 970.6 and x square will be nothing but 4. Sorry, you'll get x as 4 when you calculate it. So ni is 4, and now you can substitute it to find the number of spectral lines. So ni is 4, so 4 into 4 minus 1, that is 3, divided by 2. 2 2s are 4, okay, and 2 3s are 6. So 6, option C, 6, again option C. So C is the correct choice over here. Okay, 6. Okay, so we just use this formula. We first of all assume that nf is 1, because we assume that the atom will come to its ground state, and then keeping n initial as x square, okay, n initial as x, we solved this equation, we found the value of x, and that x is our n initial, and that n initial we substituted over here and got the answer. Okay, let's move to the last question for the day. So question 14, the last question for the day. Okay, so in this question you are given different energy levels A, B, C. Okay, and their order is given. C is the highest, B second highest, and A is the last. Okay, now when there is a transition from B to C, okay, sorry, from C to B, the wavelength of the photon that is emitted is lambda 1. Similarly, when there is a transition from B to A, the wavelength of the photon is lambda 2 in this case, and when there is a transition from C to A, the wavelength is lambda 3. The simple thing that you are supposed to do over here is to find the relation between lambda 1, lambda 2 and lambda 3. Okay, this is a question which has repeated over the years in 2011 and in 2007. Okay, so let's try it. Okay, so the only thing that we are going to use over here is the energy relation. Okay, the energy difference is basically hc by lambda, right? So that is how the energy of photon is given, right? Delta E is basically hc by lambda. Okay, So in first case, you can see the transition is from C to B. So EC minus EB, okay, EC minus EB, this has higher energy. EC minus EB will be HC by lambda 1, right? H and C are constants, okay. And for this one, if you see, it's from B to A, so EB minus EA, right? B is greater than A, and that will be HC by lambda 2, okay. Now for this one, we can write the same thing. It will be EC minus EA, right? So EC minus EA, that will give us HC by lambda 3. Now we have to manipulate these three equations and somehow get the relation between these three, okay. So if you see, if we can add this two, right, EB will get cancelled, the middle thing, right, and we'll be left with EC minus EA, which is the left hand side of the third equation, okay. So let's write, let's add first and second equation, okay. So by adding first and second, we get EC minus EA, right. So the EB will get cancelled, EC minus EA, that will give us HC into 1 by lambda 1 plus 1 by lambda 2. I've just taken HC common in both of those. Now EC minus EA, we know that it is equal to HC by lambda 3 from equation 3, okay. And here you'll have HC upon, here you can take the LCM, lambda 1 lambda 2 into lambda 2 plus lambda 1, or I can write lambda 1 plus lambda 2. Okay, HC will get cancelled, and lambda 3 you can just take the reciprocal now. That will be lambda 1 into lambda 2 upon lambda 1 plus lambda 2. Okay, and where is that? Option D, right? So option D is the correct choice over here. Okay, I hope this was very simple. We just used this relation, right, and then manipulated it wisely so that we could find the relation. Okay. So that's all for from today's class. I hope you enjoyed it. If you did enjoy it, smash that like button, and remember that the best part about life is keep enjoying physics.